Hello and welcome to Workshop 4 today on March 1st. My name is JD Cremini and I'll be running today's Vex Robotics workshop for middle school. Alright, so let's get started. So here we have the C-STEM Challenge Academic Year Pacing Guide, which show where we should be right around this time for the robotic solution. And you should be constructing the prototype design. So students will construct their prototype based on their robotics project design solution. Now, recall that last time we briefly talked about the limit switch, which sends a signal to the microcontroller when it is triggered by the bending of its flexible metal arm, and the bumper switch, which sends a signal to the microcontroller when it is triggered by impacts. So now we'll review two quick videos that will show you how to configure sensors like these two, as well as show you how the limit switch can be used to control the robot's arm. Now, the code that is used to implement the bumper switch will be the same as that is used for the limit switch that will be shown in the video. The only difference is what you will command the robot to do in response to each sensor being triggered. So here we'll start the first video about configuring sensors.
In this lesson, you will learn how to configure the sensors attached to your robot, and why doing so is important. The VEX Cortex enables you to incorporate a wide array of sensors into your robot, providing valuable sensor feedback for intelligent decision making. There are 8 analog sensor ports for sensors like the line follower, potentiometer, and accelerometer, and 12 digital sensor ports for sensors like the limit switch, shaft encoder, and ultrasonic rangefinder. In earlier lessons, the configuration steps we followed with the motors connected to the robot were optional, done only to make the task of the programmer easier. Only motors can be plugged into the motor ports, so Robot C can accept default names, like Port 2 and Port 3. Since the Cortex allows a variety of sensors to be connected, and each type of sensor works differently, configuring them is not optional. Our robot model has 2 shaft encoders, an ultrasonic rangefinder, a limit switch, and a potentiometer. The limit switch and potentiometer will allow us to fine-tune our control over the robot's arm, so let's configure them. Begin by opening the Minefield Retrieval Arm Control program from the Remote Control section. Save it as Fine-Tuned Arm Control before making any changes. Now, before we can incorporate feedback from the limit switch and potentiometer in our code, we need to tell Robot C what types of sensors are connected and to which ports. Begin by opening the Motors and Sensor Setup window. The limit switch is a digital sensor and is plugged into digital port 6 on the Cortex. So select the tab labeled VEX 2.0 Digital Sensors 1 through 12. We need to give the limit switch a descriptive name that we can use to reference it in our code. Like motor names, sensor names must be all one word, not already reserved by Robot C, and contain no special characters. In the name text box next to digital 6, type front limit, and set the sensor type to touch sensor from the drop-down menu. Now, the potentiometer is an analog sensor, connected to analog port 6. Select the VEX 2.0 Analog Sensors tab. In the name text box, next to input 6, type arm pot. And set the sensor type to potentiometer from the drop-down menu. As a side note, if you're ever unsure whether a sensor is analog or digital, you can use these drop-down menus as a reference. Robot C will only allow you to configure analog sensors in the analog ports and digital sensors in the digital ports. Press OK to finalize your changes. New Pragma configuration statements will appear at the top of your program, displaying the sensor port, name, and type. With the sensors configured, you are now able to incorporate feedback from them into your code. In this lesson, you learned how to configure different sensors for the Cortex using the Motors and Sensor Setup window.
Okay, the first video is complete, so now we'll view the second video.
limitations of your robot's arm is that it can get too low and hit the chassis, or get caught on other objects in its environment. In this lesson, we will use feedback from the limit switch to prevent the arm from over-lowering. But first, a few details about the limit switch. The limit switch is a digital sensor, plugged into digital port 6 on the VEX Cortex. The actual sensor is the small, black button below the larger metal arm. When pressed, the limit switch provides a sensor value of 1. When released, it provides a value of 0. The fact that the limit switch is either pressed or released, 1 or 0, is what categorizes it as a digital sensor. Open the fine-tuned arm control program if you don't already have it open from the previous lesson. Our goal is to prevent the arm from over-lowering, so we need to focus on the portion of our code that controls lowering the arm. Here, the second if statement checks if the down button in group 6 is pressed, and lowers the arm if it is. We still want the human driver to control when the arm is lowered, so we can't simply replace the existing condition with one that checks the limit switch. Rather, what we really want is a condition that checks if the human driver is pressing the down button, and checks that the limit switch is released before lowering the arm. Well, the keyword here is the word "and". In programming, when you want to check multiple conditions before deciding to run a body of code, you can use what are called logical operators. The AND logical operator allows you to combine two conditions, and evaluates the combined pair as true only when each individual condition is true. Place your cursor just after the existing condition in the if statement, but before the closing parenthesis. Add a space, and then type 2 ampersands to represent the AND. Add another space, and then type the second condition to check if the limit switch is released. Sensor value, front limit, equals 0. The code can be understood as, if the group 6 down button is pressed, and the front limit switch is released, lower the arm. Note that the AND can only be used to combine two complete conditions. Let's try it out. Compile and download. And run. Remember that this program requires you to press the down button in group 7 as a remote start, and that you only have 90 seconds of remote control over the robot. Now, as you lower the arm, releasing the group 6 down button or pressing the limit switch will stop the downward movement. In this lesson, you learn how to incorporate feedback from the limit switch to improve your control over the arm, and learn that the AND logical operator can be used to combine multiple conditions. Move on to the next lesson to continue to fine-tune your control over the arm using the potentiometer.
Okay, the video's complete, so now we will continue. So the next topic of today's workshop is timers. Timers can be thought of as time sensors or as stopwatches, and timers keep track of time while other code is running. The VEX robot is equipped with 4 timers labeled T1 through T4. So to use the timer, you first have to reset it using the clear timer command, and once the timer is reset, it immediately starts counting time. To find out how much time has passed since the timer was reset, you use the time1 command shown here, where in the brackets you put the label of the timer, T1, T2, T3, or T4. Now this command is very similar to the VEXRT command that we studied before, and just as the VEXRT command accesses the value of the specified channel, the time1 command gives you the amount of time in milliseconds since the specified timer was last reset at the moment that you run this code. So recall that each round of the robotics competition of the C-STEM challenge is 2 minutes and 30 seconds. If the robots continue to move after this time limit has passed, none of the actions after the point will count towards the team's score. A timer can be used to make sure that your robot stops receiving commands after the competition round has ended. The following code is an example of how a timer can be used to make the robot stop accepting commands when the competition round has ended. So here you have task main from port, and then you have the clear timer command followed by the while loop condition, and inside the while loop you have 2 commands for the motors, and then once the while loop ends you set the motor power levels equal to 0. So let's dissect the code line by line. Here you have the clear timer T1, which just resets the timer T1. Then the condition of the while loop, where you use time 10 says that it'll repeat the commands within the body of the loop until 15,000 increments or ticks of 10 milliseconds each have passed since T1 is reset. Now notice that here we use time 10 instead of time 1. The reason why it's important that you use time 10 is because each time command, whether it's time 1, 10, or 100, only counts about 17,000 ticks. And each tick is worth how many milliseconds that the timer specified. So time 1 can record up to about 17,000 ticks of 1 millisecond, which is only about like 17 seconds. But, or so. And so that's not, the time 1 command won't give us enough time to count the entire duration of the round. So we need to use time 10. And here at the bottom I have the math that was used to calculate how many ticks would equal 2 minutes and 30 seconds. So that would be 15,000. So which is why you say saying time T1, saying the while loop continues until time T1 hits 15,000 ticks, the same as saying that the while loop continues until 2.5 minutes have passed since the timer was reset. Now here you have the commands within the while loop, and this states that as long as the while loop condition is true, you map the vertical positions of the remote control joysticks to the robot's motor power levels using a 1-to-2 mapping. And then once the while loop ends, we have these two commands that say the motor power levels equal to 0, which makes the robot stop moving, and then it ends the code there. Now, although using timers can be helpful in ensuring that your robot does not accept commands beyond a certain amount of time, there's still one flaw in the programming that we have covered so far for the timers. So think about this. How does the robot know when to reset its timer and begin counting seconds? Now, running our current program will cause the robot's timer to reset as soon as the program is run, which means that the timer will reset as soon as the robot is turned on. Now, this is not ideal, however, because suppose that there is a short time left between when you turn on your robot and when the competition round actually begins. So, for example, say you turn on the robot on the field and then you have to get off the field and wait for the ref to call for the time to start. The time left between you start turning on your robot and the round starting will come out of your robot's 2.5 minutes, which means your robot will stop accepting commands before the time is ended. And this is a problem because if your robot stops accepting commands before the time ends, you'll lose opportunities to score points. And so this problem needs to be solved. And one solution is to use your remote control to signal when the robot will reset its timer and begin counting time. Now this method can be applied by adding an idle loop to your code that will only end when one of your remote control buttons is pressed. An idle loop is a loop with an empty body. So for example, here we have a while loop for 2.5 minutes after time T1 is set. And inside it you have the empty body, which means that for this time the robot will not accept any further commands. Now, an idle loop will cause the robot to, and it's important to know that you need to place the idle loop for your situation at the beginning of the code, because the idle loop tells the robot not to accept any further commands. It doesn't tell the robot to literally do nothing, which means that if you have the robot power level set right before you activate the idle loop, the power levels that the motors were set to will stay at that level for 2.5 minutes. I mean, if you have your robot going forward at full speed and then you activate the idle loop, it'll keep going forward at full speed for 2.5 minutes straight. So you have to place the code shown here at the beginning of the task in Robot C if you want to make your robot wait until you press the down button in Group 7 on the remote control before it accepts any further commands. So it's critical that you put it at the beginning of the task. Alright, so now I would like to talk about a few details regarding the game pieces that will be used in the Middle School Robotics Challenge. So, as you know, the Objective 1 involves the transportation of the water purification system. And the game piece that will be serving as the water purification system is this bottle/snack container that's made of plastic. And this thing has a height of 7 3/8 of an inch. And as you can see, the diameter shifts between the height. At the very bottom, the diameter is 2 15/16 inches. At the very top, it's 3 5/16 inches. And at the smallest diameter within the body, it's about 2 9/16 inches. And it varies within the height between those levels. Now, in Objective 2, you have to fill in the water inside your geometric printed container and transport that across the field. Now, the game pieces that will be serving as your water will be the styrofoam balls shown here that are 2 inches in diameter. So these are going to be the pieces that you have to try to fit into your container as you transport it from one side of the field to the other. Alright, that's all I have today. So if you have any further questions, you can chat me live on CSTEM Break right now at the end of this presentation, or you can email me after that at tech@cstem.org, and I will get back to you as soon as possible. And other than that, thank you for attending, and I'll see you again for Workshop 5 on March 29th.